afternoon. Welcome to the 9th Monte and Usha Ahuja Distinguished Lecture. I'm Srinivasan, and it's a pleasure to say a few words about the Distinguished Lecture Series and also about our speaker. The lecture series is supported by Monte and Usha Ahuja, both highly accomplished graduates of The Ohio State University. And they set up the series to attract highly accomplished individuals, such as our speaker today, to showcase their work in engineering and science. And today, it's a pleasure to have with us Professor Francesco Borrelli, UC Berkeley. And I'll say a few words about Francesco. He's currently a professor in the Department of Mechanical Engineering. He's the author of many highly regarded publications in the field of predictive control. He directs the MOM Predictive Control Lab, and with a focus on automotive applications, energy-efficient building system applications. He's also the co-director of the Hyundai Center of Excellence in Integrated Vehicle Systems, Vehicle Safety Systems and Control. He's got a number of recognitions. I'll mention a few of those: the NSF Career Award, the IEEE Control System Technology Award. He's an IEEE Fellow, and he received the Industrial Achievement Award from the International Federation of Automatic Control. He has served as a consultant for many major international corporations and was the founder and CTO of BrightBox Technologies, a company focused on cloud computing optimization for autonomous systems. His talk is going to focus on learning and forecasting of autonomous systems. And I would like you to join me in welcoming Francesco.
Thank you very much. Thank you for inviting me here. I had a wonderful 24 hours, day and a half. Great talks with wonderful colleagues here. It's Friday afternoon. I'll try to keep it light and give you an overview of the things I've been doing over the past 10 years. The talk is focused on learning, and I come from a place where people have overpromised learning technology. They claim that you can solve, with learning you can have self-driving cars, you can have robot manipulating cubes, you can have robots walking in down robots picking objects. The fact is that if you just focus on the self-driving cars alone, we have, and this is investment, not the government funding, this is the industry funding. And this number was from last year. We already spent $80 billion, and there's still not a self-driving car today without a safety pipe. Okay? It took $25 billion, which is roughly $150 billion to send a person on the moon. Okay? So if you compare what we overpromised and where we are now versus with things that we really done, there is a big mismatch, okay? And so I used to give these talks where I was very negative about the area, and I've tried to tone it down, so I've decided to not criticize the hype of learning, okay? But actually focus on where can it be beneficial and my definition of learning, okay? And so here's the structure. I'll start with my background. I'm a control engineer. I'll tell you the things that I focused on, that where constraints and prediction are relevant, how you can bring learning into this. I'll give you my classification in the sense it's not widely accepted, it's just a way for explaining for people outside the area what do I mean by learning. Then this will be the only technical part. Will be 15 minutes on a technique that we have developed 5 years ago. It's super simple to explain, and I'd like students to try it out. Then I'll conclude with show some applications where I have successfully applied learning and conclude. Okay? Let's start. So before I start, you can, most of the materials, all of the materials on our website, mbcberkeley.edu. There's a new trend of conference on learning and control. The next one is in Berkeley, California, COVID-19 permitting. So if it will happen, will be in June. And then there was a workshop, a week of workshop in UCLA on learning and control. If you go on these two websites, I'll post the slides. They're actually videos of wonderful speakers in the area. Okay, so the videos and presentations and slides. You will see a lot of videos, some collected over the past 3-4 years. The material, the technical material presented is from Ugo Rossolios at Caltech, Moni Moich, a lot of our current students. The applications, there's really a lot of number of people that have helped me over the years, and sponsors. So let's start with the pendulum. Okay, I teach this, and I use this in class as a wonderful example to explain how to linearize, how to abstract the system, how you compute the equilibrium point, what is a Lyapunov function. Okay? If you take what I teach to my undergraduate students and then I go back to this complex sample, they can use a lot of what we teach here in the high-level control strategy for one critical reason. The control technology we teach today, the methods, actually means constraint satisfaction. These examples are full of constraints, contact constraints here, collision constraints here, that do not really are part of this control design. Okay, and so I decided to change the example. I want to teach a class, I don't teach it yet. So I want together with the panel, I also want to teach the ball in a cup example. Okay, I'm going to, it's very simple. You take a cup and you want to swing, you move the cup so that you want to get the ball in the cup. Very simple. It's actually not too far from the panel. If you think about the model, you have 4 states, position and velocity for the cup, position and velocity from the ball. You have a constraint, which is the distance for the ball in the cup has to be less than the length of the wire. And at the end, the goal is actually written as a constraint. The ball has to be in the cup at some point in time. That's the objective. Okay? And so if you think about it, none of what we teach, the equilibrium point, Lyapunov stability, really applies to the ball in the cup example. Okay? And so, because really for this problem, constraints dominate the control design. And so if you want to write this down in a disciplined way, you would do it with a classical optimal control problem. Right? You would write down the problem is minimizing some cost function, h, x is the state, which are the position and velocity of balls and cup in 2 dimensions. You are looking for a set of feedback policy, pi, okay? 0, pi 1, pi t. These are state feedback policy that link the state of the system to the action, which are acceleration on x and y of the cup. You have a model of the ball in the cup. You can use your Euler-Lagrange equations. If the ball if there's tension, then it's a nonlinear system. One rotates around the other one. If there's no tension, the ball is in free fall. Okay? You have state and input constraints. You cannot, I already told you about the constraint between the ball and the cup. Input, you cannot apply infinite acceleration. And at the end, the target, the state at some time t has to be in your target set. The target is that the distance between the ball and the cup is 0 and the relative speed is 0. If you think about this problem, and this is the word of optimal control, it is a challenging problem, even if you perfectly know the model of your ball in the cup. Okay, it is why it's hard, because it's a nonlinear optimization problem with a set of feedback policy with a long horizon t compared to sampling time. If you're actuating every millisecond and this task takes 10 seconds, that's a long horizon t, right? So what people do in model predictive control, and I'm posting this book because now it's free, you can download it. We have a 3 years agreement with Cambridge, and so you can download it for free from the web. We solve this over a finite horizon n. Now n is much shorter than t, okay? And the only difference is that I keep repeating solving these optimization problems in real time as the new state is measured. So it is still the final solution of optimal control problems over a much shorter horizon n. With the only difference that the input at time t now is the first policy evaluated the state at time t. So that is, if you ever heard a lot about NPC, NPC is just this simple equation here. It is the first feedback policy solving this finite time optimal control problem evaluated the current state. Okay? So in the world of NPC, that's a big community. There are people working on theory, on computation, and practice. The theory side, they will tell you that because you're short-sighted, things are not going to work if you don't do it right. For the ball in the cup, imagine predicting only a few seconds ahead, which forces should you apply so that you complete your task. It's non-trivial, right? Think about it. You want to bring the ball in some region from which then you can catch it. Okay? And so what will read from the theory of MPC, they'll tell you, you need to add a terminal constraint, a constraint the end of your prediction horizon, and a terminal cost, P, so that things work, so that the system succeeds in your closed loop task succeeds. This object is called a control invariant set, and this object is called a control Lyapunov function. If you pick them to be a control invariant set, a control Lyapunov function, they will, the system will end up, the task will end up succeeding. Okay? So I'll spend just a few minutes on these two sets because it'll be important when we talk about learning. A control invariant set is a set X from which there exists an input, such that the next state, this is F is your state dynamics, they link the state at time k and the input time k with the state at the next time step, is in the set itself. So you can keep, it's invariant if you can keep this set with some feasible input. So the way people compute this is, if I give you a linear system, AX with you, I give you a target set which is 0, and I give you an input constraints. You're going to say, this is classical reachability theory. You go backward, you say, what is a set of states for which there exists an input such that AX plus BU equals 0, meaning at the next step you're going to S, and HU less equal than little h, that's input constraint. So this you see here, this object is a projection. You compute this object in the projection because you need an exist, U is a set of your components. So by projecting this polyhedron, you compute the set of states that can be controlled into S. You go backwards, okay, and so if you find a fixed point of this set valid iteration, you compute a control invariant set. There are a lot of techniques to do it. It's hard. Everybody, even people not familiar with control theory here, as soon as you talk about projection, things become computationally hard, right? The other ways to do this, you can compute, for instance, with a toolbox where Jan Mitchell computes level sets of Hamilton-Jacobi-Bernoulli equations. Those are also those are also control invariant sets. Control Lyapunov function. I'm going to talk about safe set, going to be this object. Objects for which, if you are in this set, you stay there. You're guaranteed to stay there. Control Lyapunov function. They have Lyapunov function P with one additional property, that the decrease between the state and the next state, P at the next time step minus P of X, is less or equal than the opposite of the stage cost. So they are Lyapunov function that decrease more than the stage cost. Okay? Hard to compute these objects as well. Very hard. If you give you just the simplest possible case, a linear system with quadratic cost, you run your LQRX and state and input constraints. I want the state to be in a bounded set and input to be in a bounded set. You solve your LQR, then you compute the invariant set for the closed loop system. You have replaced the K star from LQR here with the technique that I showed you before. In this set, okay, then the optimal cost of the LQR is a control Lyapunov function. This is simple, although you still have to compute the invariant set in which the quadratic function is control invariant. Okay? There are so many more techniques. You can look for piecewise quadratic Lyapunov function linear. You can solve linear matrix inequality, sum of squares. The hard part is that these things are. Point is that these objects are very hard to compute. Okay? Let's assume we have computed these objects. We'll go back to them when we talk about the learning part. How do you compute? How do you find the solution to these problems? The solution of finite time optimal control problem or a set of feedback policy. You really have two completely different approaches, right? One that I called offline based, where you do a lot of work offline, you pre-compute the solution, and in real time, you evaluate the policy. And it's very easy to evaluate once you have this solution pre-computed. This is the world of dynamic programming. Okay? You have the policy, pi at 0, the first policy, pre-computed for all possible states, and often you grid the space and you look for piecewise constant policy. That's the most common approach. And we know that if you try to ever implement dynamic programming, you have more than 5 states, it's hopeless, so you need to resort to approximate dynamic programming, model reduction, and so on. So that's one word where you compute the policy. Okay? The other word of online-based is instead it doesn't do much offline. It sets up an optimization problem, and it computes the policy at the state with a sophisticated online optimization software. Okay, this is the world of operation research, optimization. If you have a nonlinear problem, then you can solve the integral point methods would be one choice. And we know that because your horizon is too long, you really need to do, in order to make this real time, you really need to use MPC, repeated solution over short horizon, to make it work. So you have approximate dynamic programming and MPC being the two extremes. And there's a number of techniques that are trying to combine both of them. Picture, this is, if you ever run a dynamic programming, that's how it looks like in 2 dimensions. Where it's wide, it means there is no solution, means that the state cannot be constrained to be bound in this box. You have too much inertia, you will go outside. Okay? You have find a solution here, a value function and a control policy. And you keep iterating, and this is your gridded space. Okay? That's, you end up with the policy pi 0 in 2D. And MPC will give you the value. You start from a state that you measure, and will give you the value of the policy along the closed loop trajectories. It's very different. I know what is the best thing to do here, 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 here. I don't know anything about everything else here. Okay? So, this has been 20 years of done research on this. There is a long list of people trying to make online software and faster and combine them with offline methods. Ask people the details. We had a very interesting, going back to analog computing. This is, I think, is still the fastest online quadratic programming software. Is a pure analog computing computer, which we did 2 years ago. It was from Sergey, who's a Google now. But I want to show you an example, which is not from my lab, which is, SpaceX, who's landing the Falcon 9 with CVX. Okay, CVX Gen is a tool from Stanford. It allows you to solve convex optimization problem in real time, how to compute the embedded software to go on the control unit, and that's the way these things are landed. Okay, so I think you guys are lucky, the students here, because when I was a student, I didn't have access to all this software. Beautiful software, you can make companies out of this. They're very robust, reliable online optimization. Okay, in practice, what happens? In practice happens if let's take an example. Take self-driving cars, because I like cars, and this is, you have seen the classical setup with LiDAR in computers. And somewhere between sensing the environment and controlling the actuator, there is some form of MPC. Even if people don't call it MPC, replanning, recomputing, it's in there. And the reason is simple, because you have a scene of the environment, you need to predict, okay, where objects are going, you need to take an action, and then repredict the game. Okay? And that is really what MPC does. Okay? So somewhere between planning your behavior, motioning your plan, or following your path, you need to use MPCs. And each company has a different architecture. But the reality is that when you try to run this in the order of milliseconds, you don't have a lot of options. Okay? And so remember the environment set and the terminal cost, hard to compute. It's a linear system, objects are moving all around you. You tune the horizon and you pick a tailored terminal cost. For instance, I've seen a lot of people collecting data how humans drive, okay, and actually using that space of the road being as a target set, because somehow humans like to drive there. There must be a good reason for it. Okay. I told you to look for a set of policy over an horizon. It's hard to look for policies. Most of the time they look for piecewise constant function. Just look for a sequence of vectors. I told you all the theory, all the papers I write, I have this constraint. X is in X and U is in U. The reality is that the space, the constraints around you as you drive a car are time varying. And because your prediction, they are a function of prediction where the other cars and pedestrians are going to be, right? So this is an X of t. Not only, these predictions are uncertain. So you have some probability, the agent predictions are uncertain, so they really are not deterministic constraints, they are chance constraints. So what we'll end up doing, you have an X of t, you have probability of motions of other particles, and you have to transform stochastic constraints into deterministic constraints, but bounding the dates of the probability, okay? Skipping all the details here, but the point here is there's a lot that goes in engineering and making this work, right? And you don't use a genetic solver, you use, you exploit the structure because this is a special triangular structure. And every time you write a paper in NPC community, all the time you say, oh, you just set initial state. Somebody will give you an initial state. If there's anybody working on Observer here, you know how hard it is actually to estimate your state, especially in self-driving. Okay, so this is one of our vehicles going downtown. We actually have done tests now for over 5 years. The point of this video, I've seen many of these. The point of this, it's easy to actually run a demonstration like this. You can buy a $300,000 vehicle and you make a nice video like this. Making it robust, making it failure zero is actually the challenge with everybody's failing so far. Okay? And though it's a learning kind of, okay? And so where learning, what does it mean? It will mean that you will drive over and over and you collect more data and eventually this will become safe. Okay? So because I go to a lot of conferences, there is a mismatch between what I think is learning and what actually people are presenting. So I would say, okay, this is the way I see learning, at least from a control point of view. It's the idea that you can, in repetitive tasks, you can observe your system and you can use this data that you collect to get better. Okay, and this is our ball in the cup. This is Luca. And Luca is trying to put the ball in the cup, and it doesn't succeed at the beginning. It collects somehow information about the system, okay? And then at some point it succeeds, okay? So that is one possible definition, my definition of learning, okay? More in details, okay? I'll actually give you 3 sub-definitions. The first one is soccer, example. So this is I have video of soccer that I hope George will like. This is what a robotic computer is called skill acquisition. The kids don't know how to kick a ball mid-air at the end of the training. Okay, so you see the predictions are pretty bad. They're trying to kick the ball is already there. So at the end of the training, it's a skill they didn't have before, and then they do it at the end. Okay, called the skill acquisition. The second, when you keep kicking ball all your life, you become
Marcelo, so 3 to pick out. This is spectacular!
Okay. So this is now, not everybody can do that, but this is kicking ball mid-air all your life, then you become really, really good. So I call this performance improvement, meaning as you know how to do it, but you become better and better, according to some cost function. And then when you're really into that, you do repeatedly over and over, then you store it. Okay? And this is a body triangle. I use this to teach in class and see what feedback means for humans. Actually, what is interesting about this is not closing feedback on the touch. It's actually looking. I thought you would close feedback on the touch. It's actually looking and doesn't see the ball. Look at this beautiful movement. It's all pre-stored. Somewhere it's all there's no real-time optimization, and the reason we know why we do this, right? Because we can then use our brain for doing something else. We reduce the computational load. Okay? So oversimplified definition. If you talk to neuroscience, they say that's too simple. We actually it's more complex. We iterate. We first learn and then we become better, and it's complicated. I agree. Okay, but for this, I mean, for our communities. I think it's enough, meaning it is a good starting point because, you know, if you look at robotics, all the papers on learning from demonstration, transfer learning, try exactly to address the problem of skill acquisition. You don't know how to do something, you either somebody shows you how to do it, or you try to learn from things that, trying to move, transfer learning, things that are done in a different, similar task. Performance improvements, by far the most studied. You know how to do it, and then you have to get better. So control community will say, assume that the control environment is available. I've copied this from Paint, okay? It means there's a set from which there exists an input that you can succeed, right? So that's assumption. You know how to do it. The reinforcement learning community will say, suboptimal successful trajectory of the task from demonstrator available. You know, you have an initial feasible test, okay? The computational load reduction, this is all the word of lookup table generation, neural networks on chip. This is how to fast compute that optimization problem on the embedded platform. So I like cars as a charger here. So let's see how this looks like. The 3 forms of learning look like in our little 1 to 10 scale car. The first one is my car trying to learn how to kick buttons. Okay. And we keep repeating over and over. It's a tough problem. Everybody agrees. Nonlinear dynamics is clear, and you have to be between these two boxes. At the end, you succeed. And you have a policy, you have a logic that works only on that surface, only from that initial configuration, only for the two boxes in that location. Okay? We call this scalar precision. For performance in interrogation, this is a car that starts to raise this track faster and faster. It doesn't know what is the race line, the minimum time line. It starts from going very slow, the center line, and tries to get faster and faster. At some point, you hit the nonlinearity of the car state, right? And so here it is at the end after lap 33, okay, it reduced the factor 10x the speed. And if you see from inside, it actually gets a real racing. Okay, you'll see more of this video later. You get the maximum tire friction and as the car drives. Okay. Once you have learned how to raise, these are experimental data, to raise the race line. Okay. What you see, so the lap time versus the iteration number. The lap time goes down, okay, and then you achieve the minimum. You converge to a local minimum. What you can do is actually now stop predicting and use your local data, and you still keep the same performance. See, lap time is still the same, but now the computational time on the CPU is actually 10x lower. Okay, so same performance is 10x lower. I have now used pre-stored inputs rather than doing online optimization. Okay? So we do this with MPC techniques. It's as simple as what I showed you before. And what I want to do in the next part of the talk, tell you the simple technique that we call iterative learning MPC, dive into it for 10 minutes. I think it's useful, especially if you're frustrated with dynamic programming. Try the technique I'm going to show you. It's very simple to implement. Here's the idea. You have an iterative task. This is your state, okay, in 2 dimensions. And you assume that you know how to go from the initial state to the terminal state with some policy, pi 0. So this is a performance improvement task. I know how to do it the first time. The index, the notation here is upper index the iteration number, lower index the time. That's the stated time t of iteration 0. Once you use this data, you update your policy. Because you change your policy, the next time you try, you'll do something different. Everybody agrees with this? But it's an iterative. Let's put this setup in an iterative task, starting from the same initial state and ending the same terminal state. It applies also to more general tasks. So here it is, my stated time t of iteration 1 different from the stated time t of iteration 0, and so on. Right? In practice, what happens is if you make more experiments or more simulation, there is noise, and so it really going to look like cloud of points, right? And so even if you fix the control policy. So really these are called in reinforcement community rollouts, and this would be 2 different policies, the blue policy and the pink policy for 100 rollouts each. So you're going to have cloud of points. They're close to 1 average point here. So to make it simple, I'll explain the technique for the deterministic case. Everything that I'm going to say applies, and there are papers from my group, from other people, to the stochastic case. Okay? So here it is. The question is, in this idea of iterating and collecting more data, what does it change in my basic setup? Can I update the model? Can I update the terminal cost? Can I update the terminal constraint? Okay? And again, to keep it simple, let's assume the model is perfect. I know it, I'm not going to update it. Let me tell you how to update the terminal constraint and the terminal cost. Here's the idea. You have collected a set of data, and you know that this data, and the model is perfect, bring you here. Okay? And so I claim that this set of points is a control invariant set. You just sample. Meaning if I'm here, there exists an input, and I've stored it, that brings me here. If I'm here, there exists an input that brings here. So it's not a continuous set, it's just a set of discrete points. Okay? And the next iteration, okay, I'm going to run MPC, but I'm going to enforce that at the end of the horizon, I land in one of the stored points. So I'm going to land either here, or here, or here, or here. Okay? MPC looks ahead and says, well, the best thing to do is actually to land here at the end of the horizon. I apply the first input. I end up exactly where I predicted because I'm assuming my model is perfect. Okay? And again, generalization to robustness and certainty, they're all on our website. But I land exactly here. Here I repeat MPC again. So this blue has happened now. MPC predicted the best thing to do now is to land here. Okay? And apply. So you see what's happening as you explore. You're driven by your model, your cost, you explore. But at the end, you use this terminal cost to be safe, because in the worst case, you're going to follow exactly what you did before. So this safe exploration is something that we've been trying for over 8 years now. And at the end, you're going to get a set of points here that actually bring you in the terminal state, and they're also safe. So the general definition that the sample safe set at iteration j is the union of all your data points, which converge to the target set. As simple as this. For linear systems with constraints, you take the convex hull of them, and this is still a control environment. You just use linearity and convexity. Any point in here you'll be able, for any point in the convex hull of the sample safe set, you'll be able to drive the system to the terminal set. What about the cost function? Another very super simple idea. Now this time, I'm making pictures I'm assuming the state is only 1, because I also want to plot the cost. So the state starts at time 0 here, iteration j, and I have a sequence of points that goes to the terminal set. So it's only 1 dimension, moves along the line. Once I have a successful sequence, I can backward compute the actual cost to go to the terminal state, because I know the state and I know the stage cost. So just go backward and say, this is the cost that it takes to go on the stored realized point to the terminal set. Okay? Well, take the convex hull of all these points and take the epigraph, and use that as a cost to go. Okay? So if you think about it, just say the extension of linearization principle. I'm telling you there is a very simple way of computing cost to go. This is called a barycentric approximation. It's nothing but the epigraph of this convex hull. And you write it this simple optimization problem. You're looking for lambdas, the weights that sum to the stored state, give you your current state you are in. Okay? The sum of the weight has to be 1, and what you minimize is the stored cost. Okay? So don't try. If this is your setting, don't try neural network, don't try for this special linear case. This is the best thing to do, because actually we can prove that this gives you stability and guarantees of performance improvement. If you keep doing this, you will get better and better. So the next time step now, next iteration, you start from the red dot, it's the same state. And because you use this, because you have changed the cost to go, the policy changes. And because the policy changes, you will explore a new set of states, right? And now you're going to have a new cost function at the end. You're going to take the convex hull and the epigraph again. At the end, the Q function in the MPC setting is the function that each state x at iteration j solves this optimization problem where you weight all the cost of all previous iterations such that the sum of the weights is equal to 1 and the convex combination gives you x. You can prove that this object, not going to skip the proof, is a control Lyapunov function for if you're focusing on constraining your system. So here is my iterative learning MPC. This is, if you knew about MPC, all what I'm saying is, in addition to look for a set of policy, look for these lambdas that minimize the Q function the way I've constructed, such that you end up in the safe set the way I've explained to you before. It's a single optimization problem, because you combine the minimization of a lambda with the policy in one optimization problem. Okay? It's simple, it's clean, it's neat. Okay? For a linear system with constraints, this becomes a quadratic program. It's very effective. I'm going to show you next with examples. Okay? The theorem, if we read our papers, is a very nice paper on transaction automatic control, where we prove if you guarantee constraint at iteration j, constraints will be guaranteed at the next iteration. Your cost at iteration j plus 1 will be less or equal than the cost at iteration j. You have performance improvement. And if you have a linear system, then you actually get to the global optimal solution. Okay? If it's locally linear, you're going to get to a local linear, solution. So I was thinking maybe I'll give you, just to give you a flavor of what the proofs look like. How do you prove performance improvement? This is classical. This is a set of MPC manipulation that costs in the MPC community. You want that the cost to go to your target at iteration j minus 1 is greater or equal than the cost at iteration j. So you do better next time. At most you do the same thing with the equal. Xj is the state that collects all the data points at the previous iteration j. Uj collects all the input at the previous iteration. So here's the idea. Here how this proof looks like. First you prove that the cost, realized cost, to go to your target, iteration j minus 1, is greater than the MPC cost at the next step. The way you do this is you write down the sum, the cost is sum from 0 to infinity of your stage cost. Now you divided this into the sum from 0 to n minus 1 and stage cost, n to infinity. This x is the previous iteration that actually happened. You store that, right? Look at this object here. Now, this is nothing but our definition of Q function. It's how much it costed you to go to your target. Because MPC is minimizing stage cost plus cost function, at the next iteration, iteration j, you're going to do better than this quantity, which is the cost to end to the target iteration j minus 1. So, again, repeat, you have some costs at one iteration, say this is 10, okay? The NPC cost, the short-sighted, at step 0 of the next iteration will be less than most equal to 10, because the way I've constructed the Q function. You are not done, so I've proven this. Now you have proved the second part. The NPC cost, which is this one, 0 to n, is greater than the closed-loop cost at j to get to the target. So this is cost to go to the target iteration j minus 1, cost to go to the target iteration j. And here is again a classical control Lyapunov function trick. You do the delta between 0 to n cost and 1 to n plus 1. And this delta is less or equal than the stage cost. And the reason why you can write this inequality is because the cost to go is a control Lyapunov function. So if you are into reinforcement learning community, costs, in approximate programming, this cost to go, they are not control Lyapunov function. You cannot use this argument. They do need to decrease more than the stage cost to have this, to be able to prove that you get better and better. So you do this now between 0 to n and 2 to n plus 2, and you end up summing all the costs. At the end, sorry for the heavy notation, but the costs from 0 to n will be the sum, greater than the sum of the costs from 0 to infinity, and the limit for t goes infinity goes to 0 because the MPC converges. Okay? But mostly I don't want you to follow the math here, but give you a flavor of, the papers are easy to read because they use classical Lyapunov arguments and decrease on closed-loop costs. People ask me when I give this presentation to reinforcement learning community, how this connects to the RF community. And I've been trying to do connection, reading a lot of books. It's hard because there are so many techniques out there. First of all, the notation is hard because they don't have X and U, they have state, S, and action. Okay? But there is this, basically it's a new book on reinforcement learning and optimal control that does exactly the connection. It's a good control system magazine paper. Most importantly, if you are into reinforcement learning, the majority of the work in there works with discretized grids of states. Okay? And this is a continuous formulation. I'm not having any grid. I have constraint satisfactions. The majority of area community has barrier functions on cost, which are very hard to tune. Okay? And my function is exact, okay, at the points that you store. So again, if you're in one picture, this is the DP as I showed you before, okay, which gives you, because you go backwards and you look at all the states you have explored, gives you global property. You look them all, okay? But that's the problem of grading, okay? The iterative learning control does this. I put the background just as a reference, but only you have to focus on the dots. This is your set of points, and it's going to be optimal only at the yellow, but you have a policy in the red area. It's going to be, this is your iterations, it's going to be optimal only at the yellows, and but you take the convex out and have a policy in the red. So I have now not gridded, explored only locally, because I don't have a solution everywhere. Okay, and it's suboptimal if I move further away from the yellow dots. It's local and it's suboptimal, but it solves, in quotes, the curse of dimensionality. Okay? So it's a tough problem. It's no free lunch, but you, in this way, you'll be able to solve problem in n dimension with large n by being using local exploration. Okay. If you now are interested in thinking of what happens with noise and how robust is this, then you have to replace the dot with sets. So these are these are sets which are convex hull of all the dots for different rollouts. And the cost function, the Q function is going to be solving a minimax problem. Okay? And that's the way we enforce robustness and exploration while being to model mismatch. Let's go back to race and look at some of the applications where we have used this iterative learning MPC. I like racing because it's a simple problem. It's a minimum 10 problem. There's constraints which are your lane boundary, input constraints everywhere, in acceleration and in steering. And what I like is also that the model is tough. It is actually the simplest model, the bicycle model. Is here you have your Euler-Lagrangian equation. These are the forces to the tires, and this is just kinematic, body frame to global frame. Okay? So we all know, I don't have to teach it here, that these forces are tough, right? And these are the forces to the tires. The simplest way to explain this, these are slip angle and slip ratios, functional friction coefficient, the normal load. I'm teaching a class on vehicle dynamics, I love it. These are the forces. The simplest way to explain this is that your tire is a viscoelastic material, you accelerate and think of a spring model, right? You're going to have more force as a function of displacement. Okay, this F as a function of displacement, which is a function of the slip. At some point you saturate and the tire slips. Okay, this is a very, I talk to people that are more expert than me in this topic with cars, and we all know how hard it is to model these things, right? So this is one thing you would like to learn. It would be nice if I can skip the modeling of the tire, okay? The other thing that would be nice to skip, to learn, is actually the race line, because to compute the race line, it's a tough optimization problem, okay? So again, you have time nonlinearities that are hard and race line is hard. So here's what would be a classical approach. Is there any class teaching how to race a line here? If not, you can, sooner or later I'll write a little note about this, but there are lots of good papers on this. You would, first of all, pick a tire model, maybe a Pacheco model. Run some experiments to identify the coefficient, or by this model. Then compute the race line. Hard, you do divided dynamic programming, or big optimization problem. Okay? Once you have the race line, then you do a path following, which has to be robust to uncertainty, and it could be a PID, it could be a loop shaping controller. Okay? And so this would be the classical approach. I'm saying do this. Just solve in each time step the same problem, which is this guy here, where cost function and terminal set are updated in the way I just told you before. This is the old way, and this is my controller. Just one quadratic program, okay? Now you wonder what happened to the nonlinear dynamics of the vehicle, okay? Remember when I say there's two tricks to make this work in real time. MPC, which our horizon is short, and convexification. Otherwise you can't run on a little embedded computer. So what you have here, what we do is linearize the kinematic equation, then because you sines and cosines know how to do this, okay? For the forces this is a complex object because of the linear forces, uses a local linear regression, okay? Just with some kernel function. Basically, linear regression is a function of the features which are your state and inputs. And the kernel just is going to weight your local data. Okay? Just take local data and do local system identification. Georgia was doing this probably many years ago, okay? And so this is, yes, we rediscovered that local linearization identification is a good idea. Maybe, the way to, and the other thing that you have to do is to enforce model-based parsing. What does it mean? If in the first row here, there is no term in x dot, don't try to identify a term in x dot, right? So just use other equation to tell you which terms are zero, which one are not, okay? Well, there are people working in this area, these Gaussian processes. Local linear regression works pretty well. This is our car. This is each iteration, 18 seconds down to 6 seconds. We can spend hours looking at the race line. I told my student that if it's really learning the same software, which you can download from GitHub, should work on any track and on any car. Otherwise, not safe, right? You're playing it. So here's our big car. Beginning, starting in the center line, these are our constraints. Steering is not so good, it's learning, right? After 10 steps, this is the constraints we have. You can see the tires begin. Constraints here, okay. Quite exciting. Nitin love to do that. Nitin is at Apple now. I'm not happy, I don't like the codes. Let's go to the racetrack. Okay, let's see, this is our California proving ground from Hyundai. I'm gonna focus, this is our racetrack. I'm gonna focus just on this chicane here. And we spend hours looking at this beautiful data. It really computes the race line, and it's quite interesting too. At the beginning, it's it's boring because you have to drive center line at very low speeds, and it takes forever. But it's collecting data, right? You don't want to see this on Friday. But only that piece of the track here, the 400 section, go down to 42 seconds. Okay, this is almost. Here, you see opening, you can see cutting it from the apex here. Look at here, if you want to talk to me after this, we can look at all these traces, the braking, the curve, the apex, and so on. Beautiful, beautiful plots. Every time the students come, this is really, the question is, do we need all this machinery? Do we need to make this? Could it be solved in a simpler way? It's already very simple. It's one optimization problem. Do we need a safe set at the end of the ride, right? You do. You see this simulation. We didn't try to remove the safe set in the actual car. This is what happens in simulations. So we are fine like this. Okay, you go outside and people will get hurt. Do you need to predict to learn? It's actually an interesting question. It turns out is if you go dynamic programming, because in dynamic programming you have a gridded space and you're checking everything backwards. One step is fine. In MPC, in order to learn, this is a one-step NPC. Doesn't learn anything. Okay, so you need to predict more to figure out if there are other options. If you do one-step NPC, you'll be stuck to what you did before. So it turns out you have to predict in order for the controllability matrix to lose column rank, so that you have more options to get to the goal. Okay? Do you need to actually predict once you've learned? This is the story that I was telling before, the storage part. It turns out, remember the Q function that we store? And you minimize the value function, which has this form. This is going to have some optimal lambda. Use this lambda to weight the stored input. That's your policy. This policy does exactly the same thing as the MPC. So you could use a neural network. Now you have a stored use, right? You have a lot of stored use which are local. You can try to fit you can use any nonlinear interpolation you want. But I'm saying that's one way of doing it. We have some papers on that. But if your system is locally linear, take the lambda that minimize your cost function and use the same lambda to weight the input. And you can prove that this works and gives you exactly the same MPC policy. Okay? I'm close to the end of my talk. I want to share with you some of the thoughts on this. What is new? Every time I ask, is it really something new here? First of all, the vocabulary is new, right? I was writing papers on simulation, experiment, system ID. Now you have to use words like episodes, training, learning, skill acquisition, otherwise your papers don't get accepted. MPC is also called, I didn't know only recently, model-based reinforcement learning. It's MPC, but it sounds cooler, model-based reinforcement learning. It is true, jokes aside, it is true that the fact that to use data to compute level function is new, and at least it was not as started in the past. And if you think about even for simple linear system or mild nonlinear system, getting these rollouts and building these functions versus finding level set of Hamilton-Jacobi-Bellman equation of fixed points of projections is different. Okay, so this part, it is, I think, different. It's also different that we have today this ability of doing remote to embedded cloud architecture to upload your controller that's actually bring new lights to this learning. Okay, and you know there are lots of issues, say cybersecurity I've learned here in this university, but there are actually this type of applications that make learning give a reason to learn. Okay, and so I want to show you just I go around and try to talk to lots of companies and see who actually needs who's in need of this technology. And it's hard, right? In terms of you're delivering a product that changes with time, that you cannot start to certify. You really need to have a real benefit. Okay? Otherwise, you wouldn't do it. Here's my probably biggest industrial success. We had a startup that was acquired by Nextracker, and Nextracker builds trackers for huge utility scale solar power plants. If you have never seen them, these are huge. These are 754 megawatts. Our largest one is close to a gigawatt. Each of these little triangles, rectangles, is a tracker. This tracker is hundreds of football fields. This tracker is independently actuated and is supposed to track the sun because you have power. And so this today, thanks to our technology, you can actually upload all the control logic from the cloud to the solar fields around the world. Okay? And so you have 1 million PID per gigawatt, 1 million PID that you can record if you want. Okay? So what is if you think about, go back, what can machine learning or learning do here? It's not hard to think about it. What is machine learning successful, has been successful? I mean, mostly non-parametric perception. This is the slide of my colleague Ben Recht. And it's very good at classifying a zebra versus an elephant. And if you go back to the solar power plant, what you have here is that the optimal angle of each tracker depends on actually how much diffuse versus direct light you have. Basically, if it's cloudy, you won't be pointing at the sun, right? And also, you have to be careful not to shade your neighboring row, otherwise the whole row goes down. So what we did, what you can do now, you can put, instead of, you have two options. Either do a weather model with clouds moving on your solar field, that's a tough PD problem. You can put a camera on the sky and correlate it with diffuse versus direct light. Okay?
That's right.
It's a problem.
More revenues. Using this data can help your solar plants generate up to 6% more energy over the life of your plant. Introducing TrueCapture, Nextracker's intelligent tracker control system that combines advanced sensor, weather forecasting, and machine learning technologies to maximize energy yield for new and existing power plants. How does TrueCapture harvest up to 6% more energy? By enabling each individual tracker row to compensate for variations in geographic features, terrain, and changing weather in real time. Trackers don't always...
So it's not a video, this is a product. It's deployed out there, it's independently validated by engineering firms. We are seeing numbers higher than this, but 60% is the average of energy efficiency, and 60% on a 20 gigawatt fleet, that is a 1.6 gigawatt improvement of energy. And these are all the plants of solar that are controlled remotely by Nextracker. It's roughly 40% of the fleet in the world. Okay. Again, very simple idea. Okay, but a huge impact. It's probably less cool than robotic application, but it's out there, and somebody should have done this before, right? This is my next goal. I want to, that we can do over-the-air updates. Soon, every car, we're going to have an over-the-air update. I want to get rid of this. Maybe I'll do it, George. Let's see, I don't have much time left. It's a hard problem to get rid of this sticker, right? It's obsolete. We know that each of us drives different traffic conditions, and so on. Why we still verify these cars on a dyno test, okay? Lots of good reasons I want to sound to itself. But today you can totally take your Google Calendar, put it on a computer, and not only tell you what is actually the consumption of that car for your route, and also tell you upload the powertrain for that route, controller for that route, tune for that route, and you driving versus your spouse driving and so on. Okay? Technology is there. There's a demo, George has demonstrated this today. There's a team of United States demonstrating this. Chris Atkinson is coming here. We just have to do it. We have to convince government it's a good idea. And this was our fleet. This project started 3 years ago now. We took 5 Honda Ioniq, which at that time were the most fuel efficient car in the US, 58 miles per gallon. We instrumented with high precision fuel meters and volt meters. It has cruise control, adaptive cruise control, and steering control. And we basically demonstrated what we thought was a reasonable idea. If you actually, this is Fremont, Berkeley. If you drive and learn the traffic pattern, okay, you can do better powertrain control tailored to that traffic pattern. Okay? And for instance, in the specific case of the Ioniq, this is specific case of the Ioniq, the standard way of doing hybrid system is charge depleting, charge sustain, right? You first use everything in the battery, and then you start using the internal combustion engine. There is actually sweet spot, which is route specific, depends how long it is, depends on the traffic, and that's what the controller learns, okay? And here is 10% measured repeatedly over time or in the tests. It's right there, it's 10% of the most fuel efficient car today in the United States. Okay? So this is real, and all what you need is basically update the value function using measured data. Okay? We're also doing more interesting tests on the car driving downtown and then talking to traffic lights. As they drive, they learn the statistics of the traffic lights, and they learn the statistics of the traffic. And then the next time they do it, it will become better. Okay, and so these are our 3 cars. There's supposed to be a bear on top of this. You don't see the bear from UC Berkeley. You actually see how the traffic. See how the traffic around is homogeneous, the heterogeneous. Instead, this is quite homogeneous. You also see classical behavior accelerating, even if you know that the traffic light is becoming red, or you don't know. These cars, they know. Okay, this guy doesn't know, so it's going to accelerate. It's going to waste a lot of energy. This acceleration, you can imagine that there's a lot of savings there, right? It's clear. We should totally do this, right? These are the learned red light duration. These are these bimodal modes. And on this route, we have 8 traffic lights connected to our cars. On this route, in specific time of the day, you can get up to 40% energy with the same travel time on this specific route. These are not, by no means, this means everybody will get this savings, okay? There's an interesting question is what happens with the scale when everybody's going to use this technology. Okay, I'm almost done. I am done. I hope I've convinced you that the constraints prediction learning might be beneficial. Okay, there's some lowest hanging fruit that we can actually use and apply. We can apply this technology. The stuff for iterative learning control we have developed 5 years ago, and I keep talking over and almost tired of talking about it. It's a simple idea, so it's easy to explain, but it's much more than NPC. For instance, there is on our website we are doing what is called the hierarchical learning. When you learn how to race a car, don't learn a policy. You learn that you have to brake at the braking point, you have to turn at the turning point, you have to reach the apex. And this is why this is important, because if you take my policy and I turn the car on the same track, I don't know what to do. I don't know, it's a policy learned for that specific route, okay? So this high-level learning allows what's called generalization, so working in different environments. You can use this policy in any environment, right? So we're doing interesting work in this area. We're doing, I didn't tell how we solve the ball in a cup. It's because we have a camera and the camera is noise, so we build, as we collect more data, we build estimates of model uncertainty and measurement noise. And it's very hard to solve this problem because even if it's super simple mechanically, because what is the feasible first guess? This goes into skill acquisition, right? We try over and over, and it's quite challenging, okay? I think this guy will not succeed. Okay, this guy will at some point with the succeeding thing. The right to the right should succeed, but I don't. It's not playing. Maybe we don't succeed. I'll share the video. It's quite cool, actually. Okay. This is one of the things I'm working with the developer of this game. It's Bubble Ball, and Bubble Ball, because I'm trying to think about what are the simplest problems you can abstract and make it hard for mechanical engineers. Okay, this Bubble Ball is the ball my son plays with it, he loves it. It's a mechanical puzzle, it's 120 levels. You have to bring the ball in the target here, okay, where the flag is, and you have a set of pieces. And by placing the pieces, that's your initial configuration, some places, okay? Then you simulate, you observe, okay? And you observe, and you fail, and then at some point you succeed. Your control variable is which configuration. This is level 1. Level 100, you start putting cantilevers, you need to bounce in a place and other. It's crazy how complex it gets. How do I solve this game? So now I'm going to give you an online, it's going to be public available. I'm going to give you a control input, which is which pieces. You have up to 30 pieces, then there's wood and metal, each different materials and different behavior. And what are you going to do? Am I going to write a big Euler Lagrange equation? It's actually, I don't know how to solve this. Okay? Literally, we have an engine, we have a mechanic, we assume that the engine is following the physics well. And I have all these combinatorial possibilities, and how much physics do I use, how much data do I use? Do I start, you have access to the camera, to the images, and you also can have access to the states. So if you want to make it simple for you. Okay? But humans do this with just images, right? Maybe I need to have a model for each piece and identify the behavior, but then I need to predict where the contact happens. So I think it's something that, I mean, a mechanical environment, we should be able to solve this, no? Anyway, maybe here is Charlotte frustrated that this robot is not learning anything. Two open problems, and to conclude, we've been trying for 5 years. I can't solve racing with 2 cars based on camera. Very hard. What happened is that, I know, at some point the PowerPoint gets overloaded with videos and the memory goes, the video stops. So I have to shut it down and play the game. But here it will show the 2 cars and not being able to overtake. Vision-based localization, high speed is still very hard. I blame the computer vision guys. But I can't, we have been playing for 5 years with this. I still cannot race 2 vehicles on 1 to 10 scale. Okay? The other open problem is what happens when everybody's going to use, and really not PowerPoint, there's only one slide. What happens when everybody's going to use, okay, it's going to be a video, there's an image of a San Francisco here. It's going to use my learning control algorithm of the traffic light and George's learning control. What happens when learning is used as scale? That's quite unclear, right? Do you really get all this? Our efficiency gains are based on the prediction, then the traffic around me the next day will be the same as the previous day because my PPF now is constant, right? I've learned, I convert to some statistics. So learning at scales is actually it's an open problem. I think it's interesting. Thanks for your attention.
Thank you, Francesco, very nice. And if someone could turn the light on, maybe that would be good. We'll have a little bit of time for question and answer. I have 3 questions for you that I'll save for later.
Okay.
But please, anyone from the audience? Yes.
Yes.
Say.
The 3 cars that you showed, like they were moving in a line, with equal space. Was it a simulation or like you made it happen?
The cars?
Yeah.
No, that looks like simulation. That is a bad video recording. Anyway, that happened last week in LA. We have our test ground is the road in LA. Let's see why it looks like a simulation. Maybe because this is a drone. We paid a guy for a drone to take it. It's real.
Oh, it's real?
Yeah, that is in a row. Okay, let me maybe it's really let me close this. Let's see. Yes, I'll replay the game for you. It is real, yes. Yes.
Thank you for the presentation. My question is for example, autonomous driving application is, I think it's difficult to characterize as a iterative process. I think it's also kind of related to the slide where you talk about the generalization. Is there tricks that you can connect this, like the idea you present, the iterative learning process?
Yeah, no, very good question. So the reason why I decided to write papers and call it iterative, it's just the math becomes simpler. Okay, all what you need is a new set of data points. Okay, you need a new execution of your task. You can start from a different point and solve it, but really and go to a different object. But really, the improvement happens when you see things close to what you've seen before. Think about in any reinforcement learning, you don't learn anything if it's not close. If you play a game in one screen, then you play a game, the similar game, a totally different screen, there's nothing to learn there, right? So even if all the reinforcement learning, even if they don't present as iterative because there are changes, they are actually, the improvement happens when you're close to what you've seen before. Okay, so yes, going back to self-driving cars, what you will do there, the hope is that as you, in your commute, as you see more data, this data of the same route helps you improving your policy there. Now, what you're saying is that I could also use data from a left curve, okay, to actually do a right curve. Okay, that's the generalization part. Okay, it is much harder. Okay, our attempt to generalization, you need to somehow parameterize the environment. You need to say this is a left curve and that is a symmetry of the right curve. So to do it formally, generalization done formally, it's hard. Generalization where you say, oh, I've learned, I know how to drive in Boston, and therefore I drive in Chicago. It is mathematically hard. Okay, it is, and that's why I think going back to strategies, that's probably one easy way to think about it. Okay, you have acquired a set of low-level control system. You have acquired a set of primitive at high level. You know how to go straight, and therefore that's what you play. Right? Good question.
Can you make a connection with this? I got your next, since this is somewhat related. So 20 years ago, when I did Skip Barber Racing School, I walked away from 3 days of learning how to race a car with two basic ideas in my mind. One is you're trying to maximize the radius of the turn you make to minimize scrubbing. Okay? And the second one, the instructors kept telling us, exit speed is king. So whatever you do, yeah, you can brake late and all that. What really matters is not how fast you come into a turn, but how fast you come out. Can you translate these two things in what you learned from racing your little race car?
Yeah, a very good point. We are working on it. It is so the idea. If you think about these two rules, and most of the rules in task at the limits, okay, they actually use saturate constraints. Okay, meaning you need large curves, but you don't want to go the other side. Okay, you need the maximum axis speed, right? And so what we are looking at historical data that make constraints active. And so we believe we can do it. We have some preliminary results, okay? But I think there's also a nice work for Bertsimas from MIT where he has this voice of optimization paper where he looks at which constraints become active over the horizon and makes rules out of that. So there's what I'm saying, it's possible. I think it's the right way to do it. It's possible that they come, you can learn them by looking at which constraints become active. I don't have evidence that this is true. Yeah.
There was a question out there, yeah.
Wonderful talk. My question is related to the previous question. As it seems the motivation was regarding general autonomous driving, and the application of learning iterative control is somewhat restricted to something very repetitive. So a question has to be asked, how would you characterize different forms of repetitions in general driving? I mean, so there is this macroscopic characterization where you are characterizing on the base of a trip. But I also do feel there are many microscopic repetitions that happen. I mean, when you're accelerating, you do it again and again at different levels, power levels, turning at an appropriate radius at an appropriate speed. So do you think that these kind of repetitions can also be characterized and MPC ILC can be used for it?
I don't know. I think the question, it seems yes, okay? And the question of hierarchical learning is probably the next biggest holy grail, because there's a I don't believe in a hand-to-hand approach. And so somewhere you have learning at different hierarchical levels, and somehow they're combined, some are restored, some they get updated, and nobody's actually has the architecture. How to do that, I don't think. It is definitely, it makes a lot of sense, right? You should be able to learn the pedal position that makes you smoother, okay? And probably that's what they've learned, and that's what you play restored in order to make, and that is just a low level of your learning of the route that you should stay on the left-hand side because that's easy to turn left. Yeah, there's definitely, in our brain, is definitely what we do. It seems that that's what we do. We have no proof of that. Should we engineer the cars? To do that, it's unclear. The slide, I mean, that's a very good question. If you go, the reason why, sometimes I show that slide and say this is the old way, and this is the new way of think about racing. Very interesting discussion. Okay. Right, this is the classical approach. There's nothing, honestly, there's nothing wrong about this. It's a matter of fact. Think about you being an engineer of a company, okay? Like VP of engineering. Do you want this controller running, or you want this controller running? So here, if I have this controller running, I get a team that knows about tires. I get a team that, sure, when he has a new tires, he needs to update the model of the tires, but there's a guy that is expert. Then you have a team that knows how to do path planning, okay? Then robustness, how do you do robustness? Then you do mu synthesis here, robust loop shaping here. You do robustness at high level by making sure that the race, you shape the race line so that maybe it is in places where you have higher friction, or there is a different slope, right? Versus something, whether it's this or a big neural network, that's allows pulling data and taking an action, right? I don't even know we should engineer system today. These two slides are more provocative, I hope that somebody will say, okay, this is a bad idea. It's unclear, going back to the point, I don't know, yes, it's possible, I don't know if we should engineer it that way, or we should have a simple PID following the optimal, the smoothest braking profile. Okay, and the PID is tuned over many roads. Maybe the best option is to tune that PID over a specific geolocation, and then upload the PID depending on where people are and how people prefer to drive. So, very good question. Yes.
So when we are thinking about safe set and Lyapunov objective functions, so if you're say testing your car on a real road with real traffic, now your safe set would change with every iteration because the traffic on the road would be different in the next iteration. So how do you ensure the robustness of
You parameterize. That is the classical trick. You parameterize the safe set with respect to an environment variable, and then you robustify for uncertain in that environment. That would be a speed of an incoming object. That is quite classic, and it applies here too. Which reminds me, is that video real? The three cars. Where are the three cars? Okay, maybe there are simulators that are so good with quality, but yeah, no, this is not a simulator. That's the problem with computer science, right? Now this simulator is so good that you can, no, this is real. Trying to figure out if there is anything that is a proof that it's real. But yeah, it could be it could be a simulation, you're right. Maybe the flag. No, simulators are also good with flags. It's something that simulators are computer vision are not good at.
Well, the drone follows the first part very closely.
Yeah. Trying to think about maybe when the drone goes away, unless you simulate the whole scene, look at that, the details of that. It is real.
So
that best race line example, was it a global optimum?
Very good question. You know what? I don't know, because we can run dynamic programming. We could run dynamic programming. I've never got any of the students to make it work, and I actually tried, and it's hard. And I say, okay, I'll do it. And then I started in 6 dimensions. So the way we compute the race time, it's with an interior point nonlinear optimization. You're stuck to a KKT point, right? It's a KKT point, and who knows if it's the global optimum.
I mean, I was just wondering, like, can a Formula 1 driver beat that algorithm, you know?
Formula 1 already would beat it. Yeah, Chris Gert has already shown that, right? He can get as fast as the best. There's so much into it with load transfer and that it's not modeled there. The question is, yeah, if you had more complexity to the model, if you had more nonlinearities that you learn, would you reach that? That's a good question. I don't know. Yeah.
So, like, how many states and controls was that model containing?
It's exactly the one I showed you. There's not simpler, not harder. It is the lateral position, lateral longitudinal x, y, x dot, y dot, psi dot. We are 6. Then we have in the x and y in the global frame. It's an 8-state model. Okay, so 6 here, 7 and 8. It's an 8-dimensional model. What you do here, there's 2 things that you do. You transform this into S model, so not time but in space, and then you write it as a distance to the center line, so it becomes errors in y, error in y dot, and so on. So the classical transformation, but it's an 8-dimension. That's why dynamic programming is very hard. And I've tried actually. I've been trying for because I want to teach in my legal dynamics class. I want to give them something simple that they can run. Unfortunately, I have to install interior point methods to run this thing. On a series, you could do a circle simply, right? But if you have a real racetrack, it is a tough problem to solve.
One more question back there. Yeah, it's you, Mark.
Do you think there's have you looked into incorporating more agents into this to maybe find like a more radical solution? For example, do you think there's a possibility to incorporate traffic control agents like lights and things of that nature to then expand this to something much more radical? Like I remember seeing a simulation from way back where all the cars are passing through an intersection without lights just in time such that they don't collide with each other and they don't decelerate at all.
There is a lot of literature and research on multi-agent learning. We don't do that. My group doesn't do that. It's definitely very interesting. Actually, there is a student that now is looking into it. Very interesting idea. It's going to be even harder to prove. And now you have all of this that depends on what you're learning. It's providing guarantees is going to be even harder. But yes, it will definitely generate beautiful videos. I agree.
One more question.
I have a question regarding the FBC time horizon that you showed. So in a racetrack situation, when the car starts accelerating more and more, so does the algorithm changes the time horizon for which it's calculating so that it doesn't overshoot my constraints?
Very interesting question. The theory that I showed you, my proof of the decrease, is independent of n, as long as you explore. So there's only constraint that you have is that this controllability rank constraint. Okay, so this is an 8-dimensional. You need to. If you look ahead, I don't know what is the condition is. Say 4 steps. From 4 steps ahead, you will improve. Now, if you look further ahead, in the perfect case, okay, you will improve faster. How much your prediction affects the convergence speed of the learning is actually a very interesting question. I don't know if we are looking into it. It's a very interesting question. In the uncertain case, you know what happens, right? Then at some point, there's more uncertainty and it's not a good idea to predict further. So you actually decreases. Yeah, very good question. I don't know the answer.
Right, let's thank Professor Borrelli.